The Laplace transform of derivatives. Starting with the definition of the Laplace transform, we can derive an extremely useful result that allows us to solve differential equations. If we substitute in f prime of t as our function, we can use integration by parts to find the Laplace transform of a derivative. Substitute in our parts and bring the negative s outside of the integral. We are integrating with respect to t, so s is just a constant. A number to a negative power is equivalent to dividing by the absolute value of that power, so we can rewrite like this. And here we are left with the integral from 0 to infinity of e to the negative st times f of t, which is the Laplace transform of f of t. We can evaluate at our bounds. E to the infinity is infinity, and dividing by infinity will give us a limit that approaches 0. E to the 0 is 1, so we are left with f of 0. Rearrange and we are left with the Laplace transform of f prime of t. Again, start with the definition, but this time substitute in f double prime of t. Integrate by parts, and just like before, rearrange. Here we have the Laplace transform of f prime of t, so we can rewrite using that notation. We can obtain a result for the Laplace transform of f double prime of t, but this result contains the Laplace transform of f prime of t, which we already solved for. This allows us to expand our result into something useful for solving differential equations. We could run through the same process for f triple prime of t, and you might notice a pattern emerging. The Laplace transform of the nth derivative equals s times the Laplace transform of the nth minus 1 derivative minus the nth minus 1 derivative of 0. This result allows us to take the Laplace transform of a differential equation in order to solve it.